So in this segment, we're going to have a look at the long solenoid, and we're going to look at that now because many applications, transformers and other applications that we're going to look at rely on solenoids, and so it's useful to us to understand how that works. You'll find in many textbooks, including Griffiths, simple arguments based on Ampere's law arguing that the field inside an infinitely long solenoid is constant and the field outside is zero. I have always found those arguments to be really questionable on several levels, and so I'm going to show you how to calculate this from the Biot-Savart law and also show you a variety of symmetry arguments that I think are quite rigorous. Okay, so here's our solenoid. I'm going to give it a radius A and I'm going to give it a length L, and we're going to calculate the magnetic field inside and outside the solenoid, and we're going to take the limit that L goes to infinity. And we're going to calculate this straight from the Biot-Savart law, and let's just see how we go. So let's do precisely that. I'm going to label, as usual, I'm going to label our source points using, so in other words, the position of current elements, using an R prime coordinate, and our point of observation is going to be, whether it's outside or inside the coil, is going to be labeled by an unprimed coordinate. I'd better indicate here that these coils, these are coils of wire carrying current I, and furthermore that in our solenoid we have N turns of wire per meter. Okay, so that's the specification then of our problem. Let's set up the calculation from the Biot-Savart law. Okay, so here then is our magnetic field. I should be clear that this, of course, is a vector quantity. Here is our magnetic field written in terms of the Biot-Savart law, and now we're going to write down our little shopping list. Here's our point of observation. It includes a z hat bit and an s hat bit. Here is the vector pointing to an element on the coil. It has a z prime bit because this is a source term, and a z hat. Notice I don't need to put a prime on this z hat because this is a Cartesian basis vector and z hat is always the same. On the other hand, the s prime bit, the s hat prime bit here, has to be distinguished. Here, this s hat prime and this s hat in general are different, so I've distinguished between the two. We've done this in other problems. So now I subtract these two vectors and I generate this vector here. Of course, my K vector, my surface current density, is in the phi hat prime direction. Notice I've also labeled this with a prime. I can take the cross product of these two vectors, and there it is. And what you'll notice is that I generate a cos phi minus phi prime term out of this cross product here. Notice this is a cross product between phi hat prime and s hat. Now that, of course, will give you a vector in the z hat direction. Or in the minus z hat direction, but, and there it is right there, but it will depend on the cosine of the difference in the angles. And if you want to prove this, convert it to Cartesian, and you'll see that this is indeed true. This term here gives us a component in the z hat direction, there it is, and this term here gives us a component in the s hat direction. Okay, now given that I'm going to look at the limit that L goes to infinity, I may as well just specialize the point of observation to z equals 0 and to phi equals 0. So phi equals 0 would mean I'm looking on the x-axis, but since I have cylindrical symmetry I may as well do that. And z equals 0 says I'm looking at the center of the coil, but since I'm going to take the limit that L goes to infinity, in the limit that L goes to infinity, I have complete translational invariance. There really is no center of the coil. So for a finite coil, I may as well look at the center. Now, in addition to this piece here, of course, I'm going to need the mod of r minus r prime raised to the power 3. So let's calculate that term, and then we'll put it all together. Okay, so this is the integral then that we wind up with, and let's study the last term over here first of all. You'll notice that I have a z prime s hat term here, and this z prime is divided through, this is an odd function in z prime, and this is divided through by an even function in z prime. So this whole thing is odd, and if I integrate it from minus L on 2 to L on 2, I get 0. So in other words, the s hat term is going to go away. Now you might say, well, that's because I chose to look at z equals 0. You'll notice here that I've already set z equals 0 and I've set phi equals 0, as I said I would. And that's certainly true. This term would go away whether I have a finite solenoid or an infinite solenoid. But the point with the infinite solenoid is, if you like, every point looks like the center of the coil, looks like z equals 0. I have complete translational invariance. So I'm quite satisfied on this basis that the s hat term will indeed go to 0. The question, however, becomes this piece here. In the simple arguments made using Ampere's law, it's argued that this term here goes to 0 in the limit that L goes to infinity. In other words, the coil becomes infinitely long. And that is completely unobvious. For infinite sources, it's never obvious to me that the field goes to 0 at infinity. Think about an infinite plane of constant charge. The electric field does not go to 0 as you go to infinity. Infinite sources are a serious problem. Okay, you now, however, have the machinery to go and calculate this term. I've given it to you right here, and if you do this calculation, you can do it numerically in Mathematica, you can do it analytically in Mathematica, and you take the limit that L goes to 0, you will indeed find the infinite solenoid results, and you'll get the following. Okay, those are the classic results for an infinite solenoid. The field is constant, it's in the z hat direction, as we've described, inside the coil, and is 0 outside the coil. Now you might ask the question, is this consistent with the divergence of B being 0? How can it be true? How can I have a constant field in one region of space and a 0 field in another region of space, and yet the divergence of the field is 0? Well, once again, this is a conceptual issue, all tied up with the fact that we're taking an infinite source. So infinite sources have serious conceptual issues, number one. They have serious inconsistencies if you argue on simple terms, and really the right way to do this, in my opinion, is to write down the calculation as we have done, perform the calculation, and then look in the limit that the length of the coil goes to infinity.